So, Rafael, in your talk this morning, you mentioned something that was a big surprise to me. We tend to think that kids think in terms of number lines, that they always think of numbers placed along a line, that that's something that's natural to us. But your research has suggested that, first of all, mathematicians didn't even start thinking about number lines until much later in the 1700s. And you've done work with a tribe that actually had great difficulty placing numbers on number lines.
Right.
They would either place it at 0 or 10, like if they were asked, place 3 on the number line, they'd put it at 3 at 0.
With a small number.
Yeah, and if they were given 6, they might place it at 10, but they didn't have an idea of where they lay along the number line. And it was only kids who had some kind of training or exposure to that.
Right.
So I think, could you just talk, I think we must have a lot of preconceptions like that in our teaching.
Right.
And maybe talk about the implications of your research for teaching.
Right. Well, I think that line of research, what it says is sort of as I see it at least, is to kind of reconceive what is natural.
Right.
So there is a conception of natural, meaning it's in our brain,
Right.
or it's with us through evolution,
Right.
and so on. And there's another conception of natural, which is like in a given culture with given societal practices, that thing is frequent. So, for example, kids today using iPads, and clicking on things is a natural behavior. They learn very fast and they use it without much teaching.
Right.
But that doesn't mean it's in the brain,
Right.
encoded in the genes and so on and so forth. So, in a certain way, these studies with the number line, using historical material, but also experiments in the lab, and then also looking after other cultures that don't have the cultural practices that we're talking about, like measuring, like mapping constantly number to space to refer to quantities, and speak of it like I'm halfway through reading the newspaper, as if you're going from here to here, and that stands for reading the paper, and then you're half of it, meaning you still have another half. And all this spatialization, we take it for granted.
And you found with the tribe you're working with, they actually located numbers on places in the body.
Right, so this particular group, the Yugno of Papua New Guinea, they use numbers for other purposes, and they have names for them, and they also do body counts. So they place, they start with fingers, but then they go to toes, and then other places of the body with specific locations for those. But, so they do have numbers. It's not like other cultures that don't even have like a rich lexicon, meaning words for numbers higher than 4 or 5, for example. It would be like 1, 2, 3, many, and so on. There are many cultures like that as well, even today on Earth. So the point here is that this is a culture that does have numbers, and names for them and so on. Very distinct, 17 distinct from 16, and so on. So what we wanted to test was to see, well, if they have numbers, is it a necessary condition for numbers to be conceived that they are spatial, and spatialized along a line or something like that?
That the numbers have a location on in
exactly.
positions.
So what we found is that apparently, at least in this culture, even you could perfectly well have distinct ideas for numbers, and they're not spatialized.
They'd end up at the same place at 0 or 10, for instance. On the
they fall essentially in buckets, in small and big and things like that. So that is a very interesting finding, we think, because it sort of confirms other things that we see in historical record of mathematics. Is I said, well, mathematicians apparently invented the number line in the 17th century. If you look at Babylonian mathematics, and that's why I'm so interested in having Eleanor Robson coming for our workshop at the fields in a couple of months, is that Babylonians were excelled at number crunching and doing number operations and arithmetic and so on, and there's no single tablet that would have a number line in it. So that means that the invention, something we take completely for granted today, because it's in thermometers, it's in everywhere, in marking magnitude and quantity, is actually a human invention that now we created settings and so on, classrooms and environments where that is now natural, same way that iPads is for many kids in the industrial world. However, we have to be aware
Right.
that it's not in the genes, it's not in the something that evolved through evolution apparently.
And I think that would have huge implications for teaching, because if we assume these things are natural, then we
Right.
skip over all kinds of steps in
Exactly.
teaching them. So I've seen some research that when kids, you ask them to line up rulers, we assume they're just going to line up at the 0 and start measuring. But
Exactly.
many kids will line up at 1 because it's something you have to learn.
Exactly.
Teacher told me about one student who was using a ruler in grade 7, and when she measured in centimeters, she'd line up the 1 at the beginning and measure, and when she measured in millimeters, she'd line up the 0
Oh,
and
interesting.
measure.
Yeah.
And the teacher, and she was a really strong student, she was a good student.
Yeah.
The teacher said, why are you doing that? And she said, well, because under 1 centimeters is written, and
Yes.
under 0 millimeters is written.
There
So
you
she
go.
lined it
Right.
up differently
Exactly.
according to...
That's right. So I think this is exactly right. So there's so many assumptions and
Right.
that this sort of research, which ultimately is an empirical issue.
Right,
What are the assumptions that are warranted,
right.
and which are the ones that are not? And
And where do you
empirical
need to
research
remediate, and where do you need to
Exactly.
break things into smaller steps? Because
Exactly.
these are not natural to the brain, these are things you
No.
have to...
That's right. And when and it could be, let's say, in not as fundamental as a concept as a number line, but many other ones that involve notations for fractions or
Right.
whatever.
Right,
It could be that certain kids in inner city or another milieux and so on, they have different practices. Therefore, we may assume that this
Right.
is a natural notation when in fact it's not. It's an arbitrary thing that became a practice or a norm in certain contexts for certain people in certain moments of history or whatever.
Right.
But we shouldn't assume that that's the
Right.
case for, and so on.
That's one of, in developing our program, we've tried to always use the principle, don't assume anything, try and assess
Yes.
before you start.
That's wonderful, yes.
Try and assess before you
Exactly.
move forward with the student.
Yeah.
Because sometimes things you think are totally obvious aren't.
Yeah.
They'll have a different,
Right.
or prior knowledge can get in the way, something
That's right.
they may understand
Right.
differently can get in the way.
No, I think the really what is fundamental here is to unpack the obvious.
Right,
And disentangle the elements that are present in things that we think are obvious,
right,
and they're not. And we, so they need to understand what is obvious and then why it's obvious when it becomes obvious.
right,
Those are things that need a lot of like studying and investigation. And many of these things are empirical issues that luckily we have methods, and we're making and improving methods these days to get at those.
It seems like we're entering a bit of a golden age now with cognitive science and neurology, where we may actually really be able to
Yes.
figure out how to design curricula
I think so.
that works for kids.
Yes.
And you're involved with the Fields Institute in a cognitive science network that's
Yes.
going to try and, one of the purposes of the network is to try and help teachers understand and know what's now known about how children
Right.
work.
Right.
So that's very exciting.
Yeah, so I'm excited about that, and I think one of the, so perhaps it's not so much like, okay, here we are scientists telling teachers how things work, but it's actually to find out together, because there are many questions we have no clue.
Right.
And there are many methods in neuroscience that are over-reductionistic for methodological purposes, sometimes ideologically driven, like claims about things that being in the genes or in specific areas of
Or
the brain,
hardwired
or hardwired in the brain, like the number line, for example. But I think these days the methods are more nuanced, and also the newer generations of scientists are kind of understanding the subtleties of all these things on the one hand. And in the more behavioral side of things, we have new tools like this very digital camera we're using now for filming this interview. Well, with these relatively cheap tools now that you can get even through a cell phone, you can actually record human, for example, speech, gesture, co-speech gesture behavior down to a few, 100 milliseconds.
Right.
That was unthinkable 25, 30 years ago with like big cumbersome VHS cameras or whatever.
Right.
You couldn't share the data easily with your colleagues because you had to make a copy, or if you wanted to like rewind and play to see it again, and then finally you destroy the tape. All those things. And these days we have like a telescope or a microscope to human behavior in a way that we didn't have before. What are the hands doing when the eyes are engaged in some other things, and what is the thing shared, what's happening with in real time. And that's much more nuanced than what it was in the past. So
that,
I think is a new era, yes.
That was so interesting about your talk today, is that you found with calculus teachers, even though they were teaching this dry and very static formalism,
Yes.
they were constantly moving their hands, and
That's
they were
right.
constantly using metaphors to do with movement and place.
Exactly.
And that if you don't, but most people think, oh, that's just a secondary part of the lesson, that's not really important. But your claim is that if you don't take account of those metaphors that we naturally go to, then
Right.
you're not going to be able to make kids understand or make sense of calculus.
Exactly.
So I think that's very exciting that your research is suggesting that we can, by watching how teachers teach and
Right.
the metaphors and gestures they use, we can actually understand
Right.
what the deeper ideas are in the
Right.
that are
Right.
embedded in the brain.
Yeah, and I think the interesting thing is also the fact that, you know, making teachers understand that a metaphor and an analogy and so on, they're not merely like embellishments of something,
Right.
just there for rhetoric, you know,
Right.
capturing the attention of students and so on.
Right.
They actually constitute the very ideas they're talking about.
Right.
And that is a different step, and I
Right.
think many teachers should learn about these methods and these
Right.
results and so on. And it's still a growing field, but to make that leap
Right.
is a different thing.
And to go back to the number line, if many of our math metaphors involve movement along a line, or moving forward, or
Exactly.
positions, but the number lines aren't necessarily natural to us, they're a cultural thing. That means we have to teach those things very well.
Exactly.
Or because they aren't superficial parts of the math, they're actually how
Exactly.
kids are understanding the math.
That's right. And then usually metaphors and analogies and so on, and these mappings that we're talking about, they also they capture essential properties, but not necessarily all the properties.
Right.
Right. So if I'm let's say trying to convey the idea that I don't know, in particle physics, let's say, some particles move faster than others, and you go like this. Well, you're characterizing maybe the randomness of the
Right.
movement, but certainly not speed, velocity, and all these
Right,
other
right,
things.
right.
So, in a certain way, even when you're gesturing,
Mm-hmm.
you may be conveying things that are, quote, wrong,
Yeah.
in the sense that they're not meant to be characterized.
Right.
So in a certain way, reading a gesture becomes a technical thing.
Right.
So a discussion between two physicists talking about the particle physics this way wouldn't create a problem, because the communication and the reading of each other's gestures is
Right.
technicalized.
Right.
But when you teach, you have a very asymmetric relationship.
Right.
So you may be thinking that you say, oh, here's a random particle moving randomly, and then someone who doesn't know anything about it will say, oh, I thought they would move much faster than
Right.
that, but okay, this guy is telling me he's
Right.
moving just that speed,
Right.
and so on. So that's an ongoing thing, is that we cannot assume those things, and then all these analogies and all these mappings are going to capture part of the essence of those concepts, and we need to learn and teach and disentangle what are those parts.
Right. Well, it was really an honor to have you speaking at the conference today, and I think it's very exciting for teachers to be able to hear this level of research and to think deeply about how things they might think are natural or obvious to kids have to be looked at much more closely. So it's an honor to have had you.
Oh, thank you. It's been really it's a pleasure. I'm learning things now. I'm going to learn things this afternoon. I'm learning from the questions, and it's really a pleasure. I'm delighted, and I think the research program we have kind of overlaps tremendously with your program. So I'm delighted, and thanks a lot for thinking of me.
I hope we can also find some topics to research too.
That would be great.
So,
yeah. Thanks a lot. Thanks a lot, John.
Thank you.